Hi there, Mr. Sutton here with the AB Calculus 6-3 Extra Practice number 5 solutions on slope fields. For this problem, we're told that h is a function of x, a continuous function of x, and we want to know which slope field could represent this differential equation of h of x. So this seems kind of tricky because they didn't really give us a whole lot to go on. The key on this one is they said that h was a function of x. Well, if h is a function of x, that means that it's going to pass the vertical line test. It means that every time you plug in an x value, there's only one possible result from whatever x value you're plugging in, which means that no matter which y value you're plugging in, you're going to get the same result depending on which x value you plugged in. So there is no needing to take the y value into account at all because x decides everything. So then if y doesn't matter, that means that all of our slopes are going to look the same at each height. All that's going to change in terms of the slope is when you move to different x values, you're going to see a different slope. But the y value is not going to change how the slope behaves. So taking a look at which graph sort of follows this pattern, we see here in choice A, it's basically the same kind of sinusoidal curve repeated over and over again. Choice B, not so much. Here the y value definitely makes a difference. We can see different slopes on the same x value as we move from one y value to the other. So this is a place where the differential equation cannot be a function of x because you're getting different results for the same x value. Same kind of deal down here with C and also with choice D. Both of these cases, the y value makes a difference. You're getting different results for the same x value. So then only choice A could possibly follow this pattern. For this problem, I'm given a slope field, and I want to know which differential equation matches that. And just as a note, because it's not very clear from the picture, there are meant to be horizontal tangent lines on the x-axis, for whatever that's worth. So I'm going to start this one by basically looking at a point on my slope field and looking at the slope there and seeing what slopes those x and y values give me when I plug them into these differential equations. So I'm going to start with my favorite one, 0, 0. Since there's a horizontal tangent line here, clearly the slope is going to be 0 for this function, whatever the function is. So if we have a slope of 0 at 0, 0, let me see which of these differential equations also gives me 0 when I plug in 0 for the x and the y values. So choice A, we've got negative 0 plus 0, that's 0. B, we have multiplication by 0, also giving us 0. Same thing with C. But choice D, you got 0 over 0, which is undefined. So because that doesn't give us any kind of answer, let alone 0, choice D can be eliminated based off of the behavior of our slope field at 0, 0. So, but these other ones, not so much. So in order to kind of differentiate between these other ones, I want to have an x and a y value that are different, but I still want something easy. So I'm going to try out maybe negative 1, 1. If I look at my graph there, I'm not really sure what the slope there is, but I'm pretty sure it's positive. So at the very least, I can say the derivative at negative 1, 1 is greater than 0. So taking a look now at what happens if I have x equals negative 1 and y equals 1 in all of these different equations. For choice A, this is going to be, let's see here, we have negative 1 plus 1 is going to be 0. Negative 0, 0, so that's not correct. Choice A can be eliminated because it doesn't give us something bigger than 0. For choice B, I have negative 1 times 1. That does come out to a positive, so we can't get rid of B just yet. Now let's check out choice C. That's the only one we're trying to choose between. In choice C, I have negative 1 being squared to give me positive 1, but then this negative goes and makes it negative again. So we still have negative 1 times 1, which comes out negative. So choice C doesn't work out. It does not give us a positive slope. So we can also eliminate choice C. Therefore, by process of elimination, we have to pick choice B. For this problem, I'm given a slope field, and I want to match a differential equation with it. So I'm going to test out a few points on the slope field to see what they give me for slopes up here, and I'll see if they give me the same slopes down in these answer choices, and hopefully I can start eliminate answer choices based off of this. So let me test out the slope 0, 0, or at 0, 0. Looking at my graph here, we see that we have at least a positive slope there. I'm not sure exactly what the slope is. It looks kind of like 1, but it's kind of hard to tell. So I'm going to just say greater than 0, and we'll compare that with what we get down here. So if I do 0 plus 0 for choice A, that gives me 0, which is not greater than 0. So we can eliminate A. For B, this is going to be 0 times 0 minus 1. Well, that's negative 1, still not greater than 0, so B also can be eliminated. For choice C, we have 1 minus 0 minus 0, so that's just 1, which is a positive. C is still in the running. And for D, we have 0 minus 0 plus 1, which is also positive, so D is still working. Okay, well, let me try something else here. Now, the big difference between C and D is in terms of what's negative and what's positive. I see here that X is negative up here, but not down here. So let me just try something else where, let me just try 1, 1. That's another easy point to test. I think that should get to the bottom of what's going on here. So if I do 1, 1 and look that up in the graph, that also gives me a positive slope. Now, if I do 1 and 1 here, this is going to be 1 minus 1, which is 0, minus another 1 is negative. So that actually means C cannot possibly be the one we're looking for. Let's just test it out in choice D. 1 minus 1 would be 0, plus 1 gives us a positive. So yeah, D still works. We're going to pick choice D. For this problem, we're given the differential equation, and we're asked which slope field could represent that. So I'm going to test out a couple values in my differential equation and see if the slope field at those points that I'm testing out comes out the same. So I like to test out 0, 0. That's usually a pretty easy one. But if you look at all these different answer choices, the slope at 0, 0 in all of them seems to be pretty similar. So I don't think using 0, 0 here is really going to help me pick one of these. Let me look at another easy point, though. How about 1, 1? So if we look at these graphs at 1, 1, it looks like some of them are positive and some of them are 0. So the results of 1, 1 plugged into this differential equation ought to at least help me cut my answer choices in half. So if I plug 1 and 1 in here, I've got 1 cubed minus 1, which comes out to 0. So taking a look now at which ones do not have a slope of 0 at 1, 1, that would be choices A and C. They both have positive slopes at 1, 1. B and D both have 0 slopes, so we can eliminate A and C, but not B or D. So now we have to pick between B and D. We're going to pick another point now that seems to be different in the two cases. And just kind of looking on the same end of the graph here, I see down here at 1, negative 1, B has a negative slope, while D has a slope of 0. So maybe if I plug in 1, negative 1 to this differential equation, that'll help me make my final decision. So if I do that, let's see, negative 1 cubed would give me negative 1, minus another 1 gives me a negative. Specifically, I mean negative 2 if you want to be really accurate here. And taking a look at my two graphs, B has a negative slope at 1, negative 1. D does not. So we can eliminate D, and B is the only one that still works. On this free response problem, we're given the differential equation dy over dx equals xy cubed. Our first task is just to make a slope field for this thing using these 9 points here. I'm going to start by setting up a table, and you don't have to do this, but I feel it helps me organize things. So I'll set it up with the x values from negative to positive 1, and same thing on the y values. And I've set it up just like these dots are laid out here. So for this first column, we've basically got the x value negative 1 times all of these y values cubed. And interestingly, because we're using 1, 0, negative 1, cubing all of these things doesn't change them. You actually end up with the same thing after you cube them. So we have negative 1 times 1 basically, which is negative 1. Negative 1 times 0 is 0, and negative 1 times negative 1, or negative 1 cubed anyway, is going to come out to positive 1. Next, for this column, I'm multiplying the x value 0 by all of these y values cubed. Well, 0 times all of those is going to give me 0, so no point in really thinking too much about that. And this last one, I'm multiplying the x value 1 by all of these things cubed. So we've got 1 cubed, which is 1, 0 cubed is 0, and negative 1 cubed is negative 1. All right, time to go graph all those out. So for this upper left one, we have a slope of negative 1. So just imagine a tangent line extending from here down to here. That would be a slope of negative 1. For the 0 slopes, we need our horizontal tangent lines. And here's a slope of 1 down here. So this y-axis is covered with horizontal tangent lines. And over here we have a slope of up 1 over 1, slope of 0, and down here slope of negative 1. For this problem, they want us to do a couple things. First off, we need to find the second derivative in terms of x and y, and then based off that, determine the concavity of all solution curves for our given differential equation in quadrant 4. So let's start with the second derivative, and these are actually related. These are not two completely randomly separate things they threw into one problem here. So the second derivative, we need to take the derivative of the first derivative. For that, we are going to need the product rule. So let me set up my box and ribbon to organize all that. I've got u and v, so the two factors, x and y cubed. And down here I have u prime and v prime. So that's going to be 1. And this is going to be 3y squared. However, because you just took the derivative of y, and y is really itself a function of x, we have to use the chain rule here and multiply by the derivative of y, which is dy over dx. And we can't just stop there. They eventually wanted the second derivative in terms of x and y. dy over dx is itself a variable, and it's not a y. It's a y prime. We need to turn dy over dx into something that has x's, y's, or both of them. Well, look up here. They said dy over dx equals xy cubed. So this stuff down here can really be rewritten as 3y squared times xy cubed. All right, with that in mind, I'm going to put all this together to actually get a formula for dy, or d squared y over dx squared. So I'm going to use u prime v plus uv prime. So basically doing my ribbon going this way through. I've got 1 times y cubed, which is y cubed. And going the other way, I have x times 3y squared xy cubed. So that's going to be 3x squared y to the 5th, if I simplify that as much as I can. And this is going to satisfy this first part of the problem. We gave them the second derivative in terms of x and y. Now to figure out the concavity, I need to figure out in quadrant 4, does this second derivative come out positive or negative? And I mean, it said determine the concavity of all solution curves. So we're hoping it's just one kind of concavity, and we don't somehow have to, pick and choose which ones are concave up and which ones are concave down. So we're going to have to do some sign analysis then on our second derivative to see if it's positive or negative. That'll tell us if the original solution curves, which is basically y with no prime, is concave up or concave down. To make my sign analysis on this second derivative a little bit easier, let me factor as much as I can on this. So I see here that both of these terms have a y cubed in them that I can factor out. If I take out a y cubed, that'll leave me with 1 plus 3x squared y squared. There we go. And this will make my sign analysis a little bit easier, because if we're in the fourth quadrant, we know that the x values are positive and the y values are negative down there. So based off of that, we have two factors here. Are they going to be positive or negative? Y cubed, if you're plugging in negative y values, y cubed is going to have to come out negative every single time itself. How about the stuff in this parentheses? Well, if you're plugging in negatives or positives, it actually doesn't matter, because you're squaring both the x and the y. So no matter what you plug in whatever quadrant, this 3x squared y squared term has to come out positive. And since all you're doing is just adding a positive 1 to all that, this whole parentheses then, no matter where it is, always is going to come out as a positive number. So in the fourth quadrant, you are guaranteed that no matter what you're plugging in down there, you're always multiplying a negative times a positive, which means that overall in the fourth quadrant, the second derivative is always going to be negative. Okay, so with that said, what does that tell us about our solution curves? Well, if your second derivative is negative, that means the original function must be concave down. So in quadrant 4, all our solution curves will be concave down. On this problem, I want to find the solution to this differential equation given the initial condition f of 2 equals negative 1. So to do this, first I notice that I have an output variable, a y, in my differential equation. That is my red flag for knowing that I have to separate my variables. So I'm going to get the y with the dy and the x and the dx together. So I divide both sides by y cubed to start this process. That gives me dy over y cubed on the left side, also known as y to the negative third times dy. And I'm just rewriting it this way, so it's a little easier to take the antiderivative on the next step. Next thing I'm going to do is get rid of this dx by multiplying it by both sides. That gives me x dx on the right side. Now I can take my antiderivative. On the left side, this bumps up to an exponent of negative 2. So dividing by that, I have negative 1/2 y to the negative 2. On the right side, this is going to be 1/2 x to the second power plus c. Don't forget the plus c. To find that plus c, which we need for our particular solution, I'm going to plug in my initial condition of 2 comma negative 1. So I have negative 1/2 and then the y value negative 1 to the negative second power. Over on the right side, this is going to be 1/2 times the x value 2 squared plus c. So what do we have on the left side? Well, this is just going to be, let's see, 1 over negative 1 squared, which altogether is just 1, times negative 1/2. So when the dust settles, on the left side, we just have negative 1/2. On the right side, we have half of 4, which is 2. So c then is going to be negative 1/2 minus 2, which is negative 1/2 minus 4 over 2, which is going to be negative 5 over 2 for the c value. Okay, so now let's go ahead and plug that back in. So we've got negative 1/2 y to the negative 2 equals 1/2 x squared minus 5/2. We're almost there. We still do need to isolate the y value, though. I can start that process by multiplying everything by 2. And actually, I'm going to do a little bit more than that. While I'm multiplying, how about I get rid of this negative as well? So I'll multiply everything by negative 2. That leaves me with just y to the negative 2 on the left, which I can write as 1 over y squared. On the right side now, this is now going to be negative x squared and positive 5. So I'm just going to write that as 5 minus x squared. I don't like writing negatives first. It just, I don't know, makes me cringe. So let's keep going then. So if I have 1 over y squared, well, I want to make sure that this is not in the denominator. So I'm going to flip both sides to get y squared equals 1 over 5 minus x squared. So that's looking a little bit nicer. And at this point, to truly get y by itself, I have to take the square root of both sides. When I do that, I normally would have a plus or minus radical, but I'm not allowed to have both of those for just one particular solution. So I have to choose between the negative and the positive radical. To do that, I look back at my initial condition, where we had a y value of negative 1. So if y equals negative 1 from the initial condition, then in general, y has to be negative for my particular solution, which means that choosing between the negative and positive root, I'm going to choose negative square root of 1 over 5 minus x squared.